So we're going to pick up where we left off on the kinetic theory. I'm going to introduce the concept of root mean square velocity, which is just an extension of the idea of kinetic energy and the equation that we got from the kinetic energy theory. So that's where I'm going to start here. So we have the equation that the average kinetic energy of a molecule is 3/2 kB, Boltzmann's constant, times temperature. And so we can set that back equal to the idea of 1/2 mv squared, and that's the average velocity squared. So all I have to do is solve for v. Okay, so that basically becomes that the average velocity squared, the halves canceled out, is going to be 3 kt. So now this is where it's a subtle thing mathematically. I'm taking the square root of an average velocity, and the average velocity is a sum of a bunch of them. So what we end up doing mathematically is getting the root mean square. Okay, so it's not the speed of any one particular molecule, but on average what they are, and that's going to be equal to radical 3 kt over m. Sorry, I forgot the m divided by m over here. Okay, so that's all fine and dandy, but the problem is for a particular gas, which we're usually interested in, how fast is a molecule moving for a particular temperature, we don't know the mass of the molecule. It's inconvenient. So it's much easier to work with that in terms of molecular mass. Because if I know it's oxygen, the molecular mass is easy to look up. It's 32. So we're going to transition from that to molecular mass. So I'm just going to show you a quick little derivation using looking at all these constants. So K, I want to get rid of the Boltzmann's constant over m. And Boltzmann's constant, if you remember from the other side, is the gas constant divided by Avogadro's number, and then I just have the m from before. And we can show you that, and again I'll do it off to the side, moles, which is n over Na, equals little m mass over molecular mass. So if I get NaM here and I cross multiply there, I see that Na times m is equal molecular mass times n, where n is the number of molecules. And since we have 1, we're interested in 1, that simply becomes equal to R over molecular mass. So this equation, in the more useful form, is that the RMS speed is 3RT over the molecular mass. Okay, so in terms of, because it's an RMS, what you see off to the side, the graph, is how the velocities are distributed based on the speed. And so there's two things that we want to note. Is that lower temperatures, okay, as the temperature goes up, the peak will do two things. It will get lower and it will spread out more. Okay, so it lowers and the distribution spreads out with more extreme, and that's important, values of speed. In other words, at the tails, you're going to see more of it than you do when you have a smaller temperature. So smaller temperature, they're more closely clustered together. Therefore, the number of molecules that occur there are going to be higher and higher. Okay, so let's look at, let's say, for example, a certain part of our atmosphere called the thermosphere. Okay, thermosphere is really, really hot, 1,000 degrees. Yet, if you were up there, you would freeze to death, because whether you freeze or warm up has to do with the amount of energy and not temperature per se. You can have a high temperature, but if your mass is so low, there's very little energy in there, and you always want to keep that in mind. So, for example, if you touch a fluorescent bulb where the gas in there is 10,000 degrees, you're not going to get burned because there's so little energy, because there's so little mass. Anyway, in the thermosphere, which is in the upper part of the atmosphere, we can look at the following. So for H2, I want to find them. So I'm just going to put the molecular mass, and that's not something you have to memorize, so I'm going to help you out there. So the molecular mass of H2, the diatomic hydrogen, is 2 grams per mole. And I want that in kilograms for the equation, so that's 2 times 10 to the negative 3 kilograms per mole. All right, so if I apply the equation, my VRMS is going to be radical 3RT all over molecular mass. Let me draw that molecular mass symbol better. Okay, so if we plug in the numbers, 3, gas constant's about 8.3. Temperature is, I got to make sure I get that in Kelvin, so that's 1273. So 1273 Kelvin. divided by 2 times 10 to the negative 3. All right, so if I punch the numbers in, I get about 4,000 meters per second. Wow, that's pretty fast. And that's because, A, the temperature, of course, but B, because we have a low molecular mass. So if we look at helium, which has a molecular mass of 4 grams per mole, I'm just going to put 4 there, I don't have to plug in an equation again. I can see that the VRMS goes by the inverse square of the, or inverse square root of the molecular mass. So since this is twice as massive, I'm going to get square root of 2 times the, or 1 over square root of 2 times the velocity. So if I take 4,000 and I divide it by 1.41, I will get 2,800 meters per second. So not quite twice as slow. And then for oxygen, O2, diatomic oxygen, the molecular mass is 32, right? One oxygen is 16. Whoops, that should be 32. And 32 is 16 times greater than the H2, so 1 over square root of 16 is 1/4, so that's going to be about 1,000 meters per second. Okay, so that's pretty significant. We've got a 4-fold difference for the lightest of the molecules. And so the significance of that is these velocities are definitely centered, right? You know, let's say somewhere here, but there's going to be a significant chunk significantly further away, and those speeds at that extreme part are going to exceed the escape velocity of the Earth, and so we have a hard time holding on to those gases. So the Earth has no hydrogen or helium in its atmosphere, primarily for that reason. Now, the next one, it says show a speed distribution, RMS distribution of O2 in the thermosphere versus the troposphere. So the troposphere is what's near the surface. And the surface of the Earth, let's say, is standard 20 degrees Celsius. Okay? So here again is 1,000. We just want to make sure you can contrast that. So for a low temperature, let's start with the troposphere. For a low temperature, we're going to expect a high peak with a narrow high peak. So something like this, which is kind of arbitrary there. And so we'll just call that the tropo. And we might label that 20 Celsius or 293 Kelvin. So at a much higher temperature, we expect it to lower quite a bit and shift to the right and be much more spread out. Okay, so there is going to be the thermosphere, and that's at 1,000 degrees. So you want to make sure you can do something like this. I've seen that before on the AP exam. Okay, so that sums up the kinetic theory. Very satisfying how we can get not only the average root mean square velocity, but relate kinetic energy to temperature.